All right, we're going to try to solve this or reduce this or use row reduce echelon form to simplify this matrix. So we'll have a diagonals of ones with every other element above and below being zero. And then our last row will be non-zero values along its column. Okay, so along the way, I'm going to show the difference between Gaussian elimination and then also Gauss-Jordan elimination or row reduced echelon form. So our end result will be in row reduced echelon form. However, along the way, I'll stop and show where Gaussian elimination stops, and then you go forward. So they're very similar, and it's often confusing what's the difference between the two. So I want to be very clear about how those two are connected, and then also how or what you do in both of these situations. So with that being said, to row reduce this one, the first thing I notice is that I have a leading one here, or a pivot, as we also call it. And so I don't need to do any like divisions or anything like that. So one of the row operations that I can do is in there change two rows. So this row two, I'm going to move it to row one. So my first move is actually going to be simply to remove row two and make it into row one. Okay, so I'm going to switch those two rows. Nothing's really changed. One, negative three, other than the position of these two rows. And this process is more than anything just tedious. It's a lot of bookkeeping, and it's very easy to make mistakes. So if you get done to a calculation and you find out that it doesn't match what you thought it would, most likely it's a sign error or transposing a number or that kind of thing. So um, be patient with yourself and just realize that that is very likely going to happen. Certainly when you get larger elements like this, and this is just a 3 by 4. So anyway, so I want to reduce this 2 to a 0. So I'm going to multiply the first row by a -2 and add it to the row 2 to reduce it. So -2 times row 1. I'm going to add that to row 2. And just for notation purposes, for me, this isn't standard notation or anything like that, but I always think of the second row that I write as the row that's going to be changing. So it kind of helps me to kind of track backwards what I've done. For whatever reason, if I need to check in if I made a mistake or something like that. So my first row is still going to be the same. So I write that here, and that kind of helps me to remember what I'm multiplying by and then adding it to change this row. So -2 times 1 gives me a -2 plus 2 is 0. -2 times 1 gives me a -2. Adding it to -3 makes that a -5. And then -2 times a -1 makes that a +2. Adding that to 1 gives me a 3. -2 times the -3 makes it a +6. 6 plus -4 makes that a +2. Yeah. And then I'm going to do the same thing here. I want to get rid of this 4. I want to make it a 0 like this element. So I'm going to multiply it, row 1, by -4. And then I'm going to add that to row 3. Okay. 1 times -4 makes that a -4, and then adding it makes that 0. -4 times row 1 times 1, sorry, is -4 again. Adding that to 1 makes that a -3. A -4 times a positive, or a -1 makes it a +4. And adding that to 2 makes that a +6. And again, -4 times a -3 makes it a +12. Adding that to 6 makes it a +18. Okay. So we have some success here. We've got our first column set to our pivot being the upper, and we're trying to get them along the diagonal here, trying to get these leading ones. So the next goal is to work on the fifth. Now I could divide each of these by 5, by divide by 5 multiplied by 1/5. I can't divide, but multiplying it by 1/5 is the same thing. I could do that and make that pivot a leading one. But I could also interchange two rows. And the reason why I'm doing it for this particular problem is, do you see how each of these elements is divisible by 3? If I exchange these two rows switch positions, then I can multiply this by a -1/3, and that'll make that a leading one, or pivot. But it will also mean that I won't have some fractions to worry about. So if that arises, if you see a common factor, you can switch the rows, and then you can switch the rows, and then you can that'll make the chances for errors reduce when you don't have to include fractions in your calculations. So coming from here to here, what I'm going to do is I'm just going to exchange row 3, I think. It's going to become row 2. Okay. Now notice if I was doing this on my own, I would also multiply this by a third, a negative 1/3 in this transition. But since I'm trying to show each of the steps, it's going to be a little bit longer than it normally would. As you get more comfortable with this process, you'll see how to start combining different steps together to make it a little bit less lengthy in its duration, both in terms of time and also in terms of the amount of steps or the things that you have to write. Okay. So like I said, I'm going to multiply by a negative 1/3 to make this leading 1. So I'm just going to change row 2 by multiplying it by a negative 1/3. Everything else will stay the same. But that'll give us the opportunity to really make this middle row a key in eliminating some of the other values. So we're getting pretty close now, which is exciting. Okay, so now you can see how that makes it a lot easier, and I don't have any fractions or anything like that. So what I'm going to do is I'm going to eliminate the top one first. So to do that, I'm just going to think about um, multiplying row 2 by a negative 1 and adding it to row 1. And you should note that this first term here is not going to change because 0 times that, it's not going to change anything. So that'll be the same. This is going to be, I guess I should write 0, 1, negative 2, negative 6. So negative times a negative 1. That makes it a negative 1. I'm adding it to this one, so that makes it 0. Then negative 1 times negative 2 is a positive 2. I'm adding it to that negative 1, so that's a positive 1. And then negative 1 times a negative 6 makes that a positive 6. Adding it to that negative 3 makes it a positive 3. Okay. And then down here, I want to get rid of this negative 5. So I'm just going to multiply row 2 by positive 5 and then add that to row 3. All right. So this is going to change. This is 5. 5 times 1 is 5. Adding it to that makes it 0. Negative 10 plus 3 is a negative 7. And let's see, a negative 5 times negative, or 5 times negative 6 is negative 30. 30 plus 2 is a negative 28. Okay. All right, so if I pause here, this would be where we stop for Gaussian elimination. So if we're doing Gaussian, if I can spell, that would be helpful. If we're doing Gaussian elimination, I would stop here and I would start back solving the system. So I'd have negative 7, call it z or whatever variable you want, is equal to negative 28. And you would start back solving here. So this is Gaussian elimination. You're done at this point. You go from this point, and since it's upper triangular, do you see the triangle kind of there, right? The bottom triangle of zeros along the diagonal with the leading ones. That's when you know you're doing Gaussian elimination. For reduce echelon form, we're going to continue this elimination until our if you kind of think of it as a matrix like that, what we call the identity matrix, meaning it would be a diagonals of ones, every other element would be 0. Okay, so that's the difference. All right. So to do that, I mean, we're pretty much done. I want to make this element a leading one along the diagonal. So going down one more step, I'm going to multiply row 3 by negative 1/7. Okay. So nothing else has changed. What we will find is that negative 28 divided by negative 7 or multiplied by negative 1/7 is going to give us 4. So that tells us then that the value there is 4. And okay, now we're going to use this row 3 to eliminate these elements here. So we have 2 more eliminations to do with the Gauss-Jordan elimination or the row reduced echelon form. Okay, so to do that, I'm going to multiply row 3 by 2 because I want to get rid of this one here and then just add it to row 2. So we have 0, 0, 1, 4. And that's going to be 0, 2 times, and 0. And then, that's not 0, that's 1. This is 0. 2 times 0 plus 1 is 1. And then 2 times 1 is 2, plus negative 2 makes that 0. 2 times 4 is 8. 8 plus a negative 6 gives us a 2. Okay. And let's say I want to get rid of this one here. So I'm going to multiply row 3 by negative 1 and then add it to row 1. Okay. So 1 and 0, those won't change. This is going to become a negative 1. Negative 1 plus 1 is a 0. Negative 4 plus 3 is a negative 1. Okay, and so we've arrived at the row reduced echelon form. So here's the format for row reduced echelon form. Here's where we would start with or where we would stop with Gaussian elimination and backsolve. Okay, so let's just check it and make sure that we indeed get the same result for both directions, okay? So if I took it from this, assuming that we were doing Gaussian elimination, I would start backsolving and say, look, I have negative 7 times z equals negative 28. So I'm going to divide both sides by negative 7, and that gives us then that z is equal to 4. Going back to the next equation, I have y minus 2 times z is equal to negative 6. All right, well, if I plug this in, I'm going to get y minus 2 times 4 equals negative 6. Okay, so then this is y plus, sorry, y minus 8 equals negative 6. So if I add 8 to both sides, you get y is equal to 2. So now we have 2 of them. And now I can go back into, actually I can go directly to this one here and say, look, x plus z is equal to 3. But z we saw was 4, so this is going to give me x plus 4 equals 3. So subtracting 4, you get x is equal to negative 1. Okay, so the Gaussian method, once you have the bottom diagonal, I don't know how to say it better, equal to somehow you sub back in and to get back up to the original. In row reduced echelon form, you continue with the elementary row operations until you get the diagonal. This right there was what we would call the identity matrix. Okay. All right, well, I hope that was helpful, and I'll see you in the next example. All right, so we just got done doing the elimination through row reduced echelon form, and then also showing the Gaussian elimination. So now let's look and check out our results in GeoGebra. So Geogebra is a free software you can download on your device, your phone, or your laptop. It's also something that you can access on the web, and it's very powerful and does lots of really cool stuff. So anyway, to enter a matrix in, the first thing is to make sure that you have the right views. So one of the things that's kind of challenging with GeoGebra is where do you put stuff in where. So I'd like to have the algebra, the CAS is the computer algebra system, and then the 3D graphics. 3D graphics is really helpful for visualizing, especially in our class. So this is the algebra view, and I'm going to use that to input our matrix. I'm going to call the matrix A. I'm going to put capital A. It is case sensitive, so GeoGebra typically does points and vertices and stuff like that are labeled with a capital A, and then numerical values are lowercase a, so or lowercase letters, and also capital letters are for line segments. So if you're distinguishing between 2 points, so not standard, but it is pretty typical for GeoGebra. Okay, so to create a matrix, you're going to use the set notation or these curly brackets. And so the first one indicates that it's going to set, and that this second set will be for each row. So you're going to create a series of rows, and they're going to be separated by a comma. So for our example, we had 2, comma, negative 3, comma, 1, comma, negative 4, negative 4. So that was our first row. And then we're going to go outside of that bracket, hit a comma, and make another curly bracket for our second row. So we're going to import that in 1, 1, negative 1, and a negative 3. Okay, and then we're going to go outside that one, and then again hit a comma to separate the rows. And then our last row is going to be 4, 1, 2, and 6. Okay. So when I hit enter, you're going to see that the matrix A, this is a really nice visual to make sure that it does match what we had. 2, -1, 1, -4, 1, 1, -1, -3, 4, 1, 2, 6. Okay, so that looks good. Okay, so one of the small challenges is where do you put what in terms of like function and operating and stuff like that. So to do the row reduced echelon form and also knowing what the functions are called for this one, we don't do it in the algebra view. This is for computing numbers, numerical values. It doesn't handle solving like for abstract things or stuff like for a variable. If it's a numerical value, it's good, but if it's not, that's what the computer alpha system is for. So now we have the matrix A defined. Let's go over here and it's row, or no, sorry, it's a reduced row echelon form. And you'll know you have the right function when you start typing it in. Geogebra does a really good job of trying to guess what it is you're looking for. So, and if you need help, you can click on little form here. So you just do that, and it also saves some time writing. So row reduced, and the functions, though they are showing here as case sensitive, they're not case sensitive. So if you type that all in as row reduced echelon form, in all lowercase, it would still know what you're talking about. Okay, so we want it for a matrix A, and when we hit that, what we should see. Okay, so here's the row reduced echelon form. Again, this is the Gaussian elimination. We have our diagonal of ones. This is kind of like the element, the identity matrix. We have -1, 2, and 4, which is exactly what we found when we solved it by hand earlier. Now that makes right. So for the last part, one of the things I wanted to show using the technology, but also as another point of view for this particular problem, as asked in the example, is if we consider the matrix A that we talked about here earlier, one way to think about it is like a system of a 3 by 3 system, right, with 3 unknowns. So three equations, 3 unknowns equal to some value, and we're solving it. And in our previous work, we saw that we would, if we did it that way, right, with the Gaussian-Jordan elimination or with the Gaussian elimination, both, we ended up with x being -1, y being 2, and c being 4. But I wanted to offer an alternative way of thinking about it um, because this may not be any system of equations. This may be a system of um, just a system. And so one way to think about it is, and we'll dive more into this later this semester, but what if we thought about each of these columns of A as vectors? And so in GeoGebra, to create a vector, what you do is, and I'll show you how to write one out in a second, you write the vector, and if we're looking at coordinate vectors, you would start with the origin and then point to the point that you're going to. And so each of these is an ordered pair. And so typing in each of these, we're going to get these vectors over here. So you see we have this vector here. This is the first column of A. Here is the second column of A. And so you can kind of like rotate around and see where they're at in three-dimensional space. And then here is the third column of A. And then finally, our fourth column of A, which was what we were calling the answer column earlier. Okay. So if you notice, these are the 4 column vectors of our space A. And what we saw in the row reduced echelon form is that 3 of these are what we would call linearly independent, meaning they can be reduced to a pivot element. And so one way to think about how this formation of the row reduced echelon form is that you have these 3 vectors which are independent, and it doesn't matter which ones they are. It is completely arbitrary. We can uh, change these, just relabeling the variables, if you will. But we're going to think of this last row here, or this last column, as a linearly dependent variable. And what that sounds very fancy as is it's just written. In other words, I can take each of these 3 vectors, what Joe was calling U, V, and W, and I can write this vector A uh, by writing some combination of these, right? So adding and subtracting these, multiplying them by maybe some number. What I can do is I can write these and add them together to recreate this exact vector here. So I'm going to color this vector here a different color. It's currently, I'm going to color it like a bright, maybe pink. maybe green, pink. No, the green seems to stand out better. Okay, so so this green vector here is the A vector, which is the last column of our lowercase or of our matrix A. So this should be then how it's telling you each of these elements, how much of each of these rows you need, each of the column vectors. So if I multiply 1 times our first column, which was U, then I add to that a 2 times our second column of A, which is B, plus 4 times our third column, W. Okay, what you should see, sorry, that should be a negative 1 times U. So that combination of vectors should give us back exactly what you see here. And so you see B and A are exactly the same component wise, -4, -3, and 6, which is exactly the fourth column of our. So what this is saying is that it's a linear combination, what we'll call a linear combination. And you can see that by turning on and off this black vector B, it's exactly the same vector as A. So another way of thinking about this row reduced echelon form is that it tells you if any of the other columns can be written as a combination of other columns. So the leading one, so the pivot columns, or what we would call linearly independent, and they would be then the ones that could form uh, the combinations of the other vectors. Okay, well, I hope that was helpful. I'll see you in the next video.